So our problem here tells us to find the volume of the shape or of the object obtained when a hole of radius r is bored straight through the center of a sphere of radius big R. So if we draw a little diagram of this, let's see if we have our sphere here, and we're going to bore, or we're going to make a hole that goes straight through the center of the sphere. And this hole is going to have radius little r, and the big sphere is going to have the radius big R. And we want to try to find the volume of this shape. Now, one way we can go about doing this is consider the graph of a circle. So if we want the circle to be this big sphere over here, then we could have its equation be x squared plus y squared equals big R squared, where our horizontal axis is x and our vertical axis is y. So this will give us the shape of a circle. That's close enough to a circle. Okay, so what we want to do is we want to create a hole through this circle. So if we reduce this problem down to 2 dimensions, essentially what we are doing is we're creating a hole of width r through this circle of radius big R. So we're tunneling this circle through this sphere of radius big R, and this little circle has the radius little r. So one way we can create this shape here on the left is to rotate this shape around the y-axis. So imagine if we rotate this shape in pink, or this area here in pink, around the y-axis, then we get something like our shape here on the left. Now, you may also have noticed that this thing over here is actually symmetrical about the x-axis. So in reality, all we have to do is find the volume of half of this. So if we find the volume obtained by rotating this section about the y-axis, then multiply that by 2, we are going to get the volume of this object on the left without doing too much extra work. So our equation, instead of x squared plus y squared equals r squared, we can solve for y and get just the positive part of y. So if we solve for y, we get y squared equals r squared minus x squared. And when we take the square root, we only need to take the positive part, because we can multiply the volume of this area spun around the y-axis by 2, and then we can find the volume of this object on the left. So our equation is going to be y equals r squared minus x squared. And the way we go about finding the volume is by shell method, because we're rotating this around the y-axis, and we can divide these into nice cylindrical shells. So if we were to do that, then the volume of this entire shape is going to be 2 times the volume obtained by rotating just this upper portion around the y-axis. So the shell method tells us that we want our shells to go from this r, little r, all the way to big R. So we're starting here, and we're making shells all the way to here. So we have 2 pi, the definite integral, starting from little r going to big R. And then we have our variable x. So this is just the circumference of these cylindrical shells going from little r to big R. And then we're going to multiply that by the function, which is root r squared minus x squared. and we're going to take this with respect to x. So solving this, or computing this definite integral, will get us the volume here on the left. So right now, let's go about solving this integral. So we're going to move this over to a different page. We have the volume is equal to 2 pi times 2. So 2, here I'm just copying what we had on the previous page. 2 times 2 pi, definite integral from little r to big R, x times the square root of r squared minus x squared. So if we can solve this definite integral, then we get the volume. So one way we can go about doing this is letting substitution do the work. So we can let u be equal to everything inside of this square root. That way du can be equal to negative 2 dx, or negative 2x dx, which is just the derivative of this thing on the left. So solving for dx, we get dx equals, or x dx, because we have an x here. So x dx equals du over negative 2. So all we're doing is just rearranging this thing on the right here so that we can plug it into our equation later on. So we're going to keep going. The volume equals, so let's simplify this. We'll call this 4 pi, the integral. So right now, x dx can be replaced by du over negative 2. And the square root of r squared minus x squared can be replaced by the square root of u. And right now, our lower and upper limits are now in terms of u. So all we're going to do is plug in our upper and lower bounds into this equation where x is, and we're going to get u. So plug in x squared and plug in r for each of the x's. So for the bottom one, we'll get r squared, big R squared, minus little r squared. And for the top one, if we plug in big R squared, we just get 0. So what we can do now is we can take this negative 2 outside to get 2 pi, and this negative sign will multiply it into this definite integral, which all it does is just reverse the upper and lower bounds. So instead of going from big R squared minus little r squared to 0, we go from 0 to big R squared minus little r squared, and the negative cancels out. So we have root u du. So if we evaluate this, all we have to do is take the antiderivative of this because of the fundamental theorem of calculus. So in this, all this is u to the 1/2, and we just use reverse power rule. So what we are going to get is 2/3 u to the 3/2. So you can see that if we take the derivative of this, this goes down, that makes 1, and then you subtract 1 from here, you get u to the 1/2, which is just root u. And we evaluate this at r squared minus little r squared and 0. And if we evaluate this, then what we are going to get is 2 pi 2/3 r squared minus little r squared to the power of 3/2. And subtract 0 when you plug it into u, it's just 0, so it doesn't do anything. So what we get for our final answer is 4 pi over 3 big R squared minus little r squared to the 3/2. So this is the volume of the object shown here.